PCR can take you far, at least if your goal is DNA copying.
PCR stands for polymerase chain reaction, and it's a way that we can make lots and lots of copies of a specific region of DNA based on a template sequence. So if we have a template, we can specify which region we want copied using these short little pieces of DNA that we design, these things called primers. These primers are basically going to bookend the region of the DNA we want copied. And then we use this molecule DNA polymerase, which is an enzyme. It's a reaction speeder upper that's actually going to piece together the DNA letters specified by the strand that they're traveling on. And so each strand can act as a template for making the corresponding strands. Each cycle, you're going to be making a copy of each strand. And so therefore, each cycle, you're going to be making another template. And then the next cycle, you can make that use that template to make another. And so you get this exponential amplification. So where each copying cycle, you are going to be doubling the amount of DNA that you have. And we do this in cycles where we're controlling the temperature to control what step is happening. So whether we're actually separating those strands so the DNA polymerase and the primers can find access, whether we're allowing the primers to bind, whether we're doing an extension, we're actually letting DNA polymerase go to work. We can control all this by controlling the temperature. And we're doing this in a machine called the thermal cycler. Sometimes we just refer to these as a PCR machine, but you can use them for things other than PCR. But why they're really helpful for PCR is they're going to allow us to quickly change the temperature. And so we can go from really hot to separate those strands. We call this a melt step. We cool things down to allow the primers to bind. This is the anneal step. And then we raise the temperature a little, so we have an extension step where we actually allow DNA polymerase to go to work. And then once it makes a copy, we have to do this again and again. And so this is where the cycling comes in, because we have to, after each cycle, separate those strands so that they can be used by DNA polymerase in order to make the copy. But before DNA polymerase can actually go and make the copy, that extension step, the primers have to bind. And so we have that anneal step, which has to be a little bit cooler than that extension step so that the primers don't have too much energy to just float around. They need to have less energy in order to stick. The more energy you have, the harder it is to stick. And so the stronger the interactions are, the more energy you need to overcome them. And so basically what we'll talk about later is when you design these primers or when you're setting up your reaction, you're having to decide what temperature you want these various steps to be at. And this anneal temperature, the temperature at which your primer is going to, you set your primer to bind, is going to depend on the properties of the primer. And so we'll talk more about primer design later. But that's just something to keep in mind. So the temperature of that step is going to depend on your primers. And then the other thing that you're going to have to control is the length of the extension step. So typically the extension step, the temperature is going to depend on the temperature at which the polymerase works best at. So typically these are like heat stable polymerases, like thermostable, so they can work at really high temperatures. And so they typically work at like 72 or so. But the extension time, how long it has to go, depends on the length that you want copied. And so if you want a longer product, you're going to have to let DNA polymerase have more time to go to work. So some of these faster polymerases these days, it's like 15 seconds per kilobase or whatever. So if you had, say, a 4 kilobase product, you would have 1 minute extension per cycle. And then you do this over and over and over again, depending on how much DNA you want to copy. And so we'll talk more about all these details later. But first, let's just go step back and get into the basics. So to understand what's going on, we need to understand DNA structure a little and some of the terminology. So DNA is what we call directional, and when it's present in these double-stranded structures, it's anti-parallel. So by directional, we mean that one end is different than the other end. So at one end, like starting end, you have the free 5' phosphate groups, and at the 3' end, you have a free 3' OH. And these groups are kind of going to be the linking on points. And so when DNA polymerase goes and adds the letters, it does so 5' to 3'. So it takes the incoming nucleotide, which has a free 5' phosphate group. These phosphates are these are like energy. You can think of it like a clamp spring where these negatively charged phosphate groups are kind of being held together, like a tightly held clamp spring. And then when you break that, you get energy, because just like if you release the spring, something will like fly off the end. When you do this, you get the energy you need in order to link these bases together. And so this 5' The way you can remember that you're going 5' to 3' is because the incoming base is going to pay the cost. The incoming nucleotide is going to pay the cost of actually linking together. And so your strands are going to run from 5' to 3'. But when you have two strands held together, well, now these strands are going to be anti-parallel. So you're going to have one strand running 5' to 3', and the other strand running 3' to 5', if you just think about it in this sense. So basically you have one strand like this and the other strand like this. And this is what we mean by anti-parallel. And so if we write these strands out separately, however, we'd still write them 5' to 3'. But when we're looking at them in this sort of notation, one strand is looking like it's 5' to 3', and then the other strand is looking like it's 3' to 5'. But the important thing to remember with PCR is that the polymerase can only travel 5' to 3' because it has to be adding, the incoming base has to have, the incoming nucleotide has to have those free 5' phosphates in order to get added. So DNA polymerase can only travel in one direction. It can only travel 5' to 3'. And these strands are going to be anti-parallel, which means that as one DNA polymerase is moving from what looks to be like in one of these pictures, if it's moving from left to right, the other one's moving from right to left. In both of these cases, it's moving from 5' to 3'. So this can get kind of confusing. And what we're talking about when we're talking about the actual sequence is the reverse complement. So with DNA strands, you get this complementary binding where you have A to T and G to C. And this is really helpful because it's going to allow, it's what allows one strand to act as a template for making the other. Because as DNA polymerase goes along, if it sees an A, it knows, okay, I've got to put a T. If it sees a G, I've got to put a C. If it sees a C, I've got to put a G. And if it sees a T, it's got to put an A. So it knows what to add based on what is in front of it. And then what based on, well, I mean, it's not like it really like is thinking about this, but the interactions you get between the A and the T and between the G and the C are going to be specific, so that you get these kind of like, that's why you can think of it kind of like puzzle pieces that fit together. So you get these favorable interactions, these hydrogen bonding interactions. So these are just those like partial charge attractions, rather than like strong links to hold the chains together. So that's why we can unzip the strands without like taking the strands up, actually like fragmenting the strands or whatever, messing with the actual strands, because we get that complementarity. But because one of the strands is 5' to 3' and the other strand is 3' to 5', these strands, when we talk about the complementary, when we actually write out the sequence, we're going to have the reverse complement. And so this is why, because when you write the sequences, you write 5' to 3', and so your primers are going to be the reverse complement of the strands of which they match. Thankfully, if you have two strands of DNA, you can just kind of think about it as designing one primer that's going to match the sequence of one strand, and then one primer that's going to match the sequence of the other strand. So basically, this primer is just going to match this region of this sequence, and this primer is going to match this region of this sequence. But this primer is going to be the reverse complement of this sequence, and this primer is going to be the reverse complement of this sequence. So as you can see, the terminology can get kind of confusing, but you just kind of have to look and think about it for a minute. Just make sure that you're ordering what you think you're ordering. But thankfully for PCR reactions, when you're doing it so you have both strands, you just need to make sure that you have it going so that your primers are actually going 5' to 3', so that your DNA polymerase is going the right direction. Because remember, DNA polymerase can only go 5' to 3'. So these primers are going to tell DNA polymerase where to start. And then when it has that 3' OH here, this is where now your incoming nucleotide has that 5' phosphate groups that can get added on. And so this is why you're going to be going from a 5' to 3' direction. Now, in order to actually get this primers to bind, however, you need to raise the temperature so that the DNA strands will come apart. So this is where the melt step comes in. And so this melt step is typically somewhere around like 95 degrees Celsius or something. You basically want it to get really hot so that nothing's going to bind to one another. Because the most stuck things are going to be your full length products or your template. your template's going to be the most because it's got the most interaction. So if you think about maybe you have some long sequence and you're trying to just amplify like a tiny little portion of it, but you have all of this stuff that you have to unwind. That's a lot of interactions. You could have thousands of base pairing interactions. And so in order to actually get those separated, you're going to have to heat up the reaction, and you're going to have to heat it up to the highest temperature that you're going to use in the reaction. And so now, though, you have those strands separated. So now you have the strands that can each act as a template. But you have a new problem in that we need to let those primers actually bind. And now those primers, we want them to bind only where we want them to bind. So we don't want them to just bind anywhere, which means we can't just lower the temperature like this. But now we have a problem where we need the primers to bind, but we just raise the temperature so that nothing can bind. So we're going to have to lower that temperature. But we don't want it to lower it too far, or else basically the primers can bind non-specifically. We want those primers to only bind where we want them to bind. So when we design these primers, we typically design them so that they should only bind in one place. So there's software that you can use, things like BLAST, in order to try to make it so that your primer isn't going to bind non-specifically to other places. But it's not perfect, and you can get these basically primers binding to other places, especially if you're trying, maybe if you think about, okay, well, it's only going to bind to one place in my plasmid, but then your plasmid is in bacteria, and then you have to think about the bacterial DNA, blah, blah, blah. So you can get non-specific products in which this is going to make where the primers are binding to different places, places that aren't where you want, then you get a number of different pieces. You can also get things like primer dimers, where basically the primer binds to copies of itself and makes these short little products. So there's these various things that can happen if your primers don't only bind where you want them to bind. And so in order to make them bind only where we want them to bind, in addition to basically trying to design the primers so that they don't bind anywhere, that they don't have as good of opportunities to bind elsewhere, we need to make it so that we control the temperature so that those weaker interactions are going to be excluded because the temperature is too high for them. But our specific interactions are still going to be able to hold because they have tighter interactions that are going to take more energy to break. So when we talk about the energy required to separate the different things, we're talking about the melting temperature, or the TM. So the stronger the interactions between things, the more energy you're going to have to add in order to get them to come apart. So the higher the temperature. So temperature is a measure of average kinetic energy. So how much energy those molecules have to wiggle around. The tighter the molecules are held together, the more energy you're going to need to give them in order to wiggle free from one another. So if you have those really long DNA strands like we had before, we had to get the temperature really high. If you have really short things and things that are going to be less specific. So maybe if you have a couple regions that bind, they have a bunch of mismatches, but they kind of bind, they're going to be able to, you're going to be able to break those more easily at with a less energy. So you still need to give them a little energy, but not a ton. So with the PCR primer, we typically try to find this Goldilocks, where we have this, basically these are typically around 20 nucleotides or so. And we want them around 40 to 60% GC. Basically, the AT versus GC. The GC regions that are GC rich, so if you have a GC rich primer, it's going to bind more tightly. And the explanation that you probably hear most often is that G and C, they have these 3 hydrogen bonds, whereas A and T, they only have 2. The real reason why GC rich regions are stronger actually has to do with base pairing, so with the stacking interactions in that double helix. But I'm not going to get into that here. It's about outside the scope of this post, but I'll link to some more information about that. But basically, the more GC rich your sequence is, the higher the TM, and often the higher the longer it is, the higher the TM, because basically when you're strengthening the interactions, you're going to have a higher temperature needed in order to melt them. And so this TM is going to dictate what temperature you're going to set your anneal step to. When you set you want these primers to basically have a similar annealing temperature so that you can have you can set the TM so it's going to be ideal for both of these. Now, if you set the temperature too low, what can happen is that these non-specific products and these more weakly binding things can can bind, and then you get the non-specific products. But if you set the temperature too high, well, now the primers can't bind, and so then if the primers can't bind, you can't get the amplification. So that's not good. So you design this anneal temperature based on the melting temperature of your primers, and typically it's going to be around like 60 to 70 or so, depending on the composition of your primer. If you're getting a bunch of non-specific products, you can try raising your anneal temperature and things like that. There's various additives you can try. And things like that. We talked about yesterday how you can use a hot start polymerase. So basically you prevent the polymerase from actually starting until the reaction you want it to start, so that you're not getting basically the polymerase can't be amplifying anything and nothing can be binding before. I talked about yesterday how you can use like hot start PCR, where basically the polymerase can't get going until it's actually at the ideal anneal temperature. So that you don't have it making non-specific products while you're setting up the reaction. So more on that in yesterday's post, but that's one way that you can avoid those non-specific products. But anyway, so say that you got your anneal temperature to work, and now so you melted it, you raised the temperature to separate the strands. Now you anneal it, so you allow those primers to bind. And now you're going to extend it. So you're going to let the DNA polymerase go to work. And remember, the DNA polymerase is going to go 5' to 3'. And so basically what's going to happen is that in this first cycle, it's going to just keep going until it either falls off, or it runs out of time, or runs out of energy. And so basically we set this, when we're doing this extension step, we have to dictate how long we want it to go. So typically we're not really messing with the temperature of this step, because it's going to be dependent on the ideal temperature for that polymerase. So there are different polymerases that are commonly used for PCR, but these polymerases are generally, they're more sturdy than the polymerases our body uses. And so when our bodies use, they would never be stable at these temperatures. But when we have these PCR polymerases, they're typically thermal stable. And so this is going to allow it to survive when we have to do those hot steps. And then it also has a temperature it's going to be like most ideal at. And so often you might hear of like TAC polymers. This was like the conventional one, the typical one that was often used. But now there's more like modified versions that have either better fidelity, so they're less likely to make mistakes, or they have better processivity, so maybe they are less likely to fall off, or things like that. Maybe they go faster. So there are various different polymerases that you can get with better, depending on whether you want more accuracy or faster speed or things like that. And so then the temperature is going to depend on what polymerase you use. And then the time of the extension step is going to depend on how long the region that you want copied is. So even if you have one of those really, really fast polymerases, say one that goes like 15 seconds per kilobase, so it can go 1,000 bases in 15 seconds. So if you had like 4,000 base product, so a 4 kilobase, you would need to set that extension step for 1 minute. Because if you set it for shorter, the polymerases, even if it's going to run out of time before it gets to the end. But you don't want to set it too long, because now you're increasing the chances that you can have like side reactions happening if the polymerase gets bored. Because remember that if you make one template and then you're hovering up that template, now the polymerase is just if you run out of the actual template at once, if there's still other stuff hanging around, you can get non-specific products. And so typically we designed that you set the extension step to match the length of the longest thing that you're wanting to amplify in the reaction. And also you don't want to make it too long, because then your PCR cycle is going to go really long, because you're typically doing this for like 30 times or so, depending on what your goal is. Okay, so but say you set that extension time for the right length of time, your DNA polymerase now goes, well, in this first cycle, it's going to go basically until the time runs out or it falls off. But now in the second cycle, this is where we start making specific things. So we melt again, and now these newly made strands are going to serve as the template. And these strands are going to end where the first primer started, because that's where you said start here. And so that's where the end is going to be. And so now when you have the primer, so now you have remembered like other primer going, because you have that anti-parallel nature where you have one per strand. And so now this primer is going to go dictate where the start is, and this is going to specify the second end, and it's going to go until it falls off, which is going to be the place at which the first primer started. So it's really hard to explain in words, but hopefully the pictures can help you see what's going on. After you get past that second cycle, thankfully, things get a lot simpler. And so here, basically, each cycle, you're just going to be amplifying the region that was bookended by those primer start sites. And you do this again and again and again, depending on depending on your purposes. And so if you go over and 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 over, you're eventually going to start amplifying more of the side products. You have a better chance because you're basically just amplifying each cycle. You're to be amplifying things. And so you can have the buildup of those less specific products as well. And so one way that you can actually see this is if you're using something like qPCR, where basically here you're copying the strands and then you're counting how many copies you have as you go along, basically. So the fewer copies, you're measuring the fluorescence. So each cycle, basically, you have some readout of the new product being made is going to give you a fluorescent signal. And so some light given off. And then the faster that signal rises, the more you started with, or the number of cycles basically it takes to cross a threshold of fluorescence, the more copies you started with. So this is often used in things like molecular diagnostics to say like, okay, well, is this viral DNA present or something like that? And so basically, once you go to a really, really high number of cycles, you're starting to get stuff amplified over the threshold, even if you don't have anything there to actually start that specific. And so this is a way to think about it. Okay, well, you don't want to set your PCR reaction to go too many cycles, because then you're going to be starting to see that sort of thing. But if you don't go enough cycles, then you're not going to have enough product to do what you want. And so what you want is going to depend on your different purposes, such as things like cloning or qPCR, various colony PCR, various things like that you could be using. And so you can make lots and lots of copies of the DNA. A couple more notes. Often when we're doing this in the thermocycler, we're using a heated lid. This is basically to make it so that the water doesn't all escape from your reaction when your reaction gets really, really hot. So remember, we get really hot to separate those DNA strands, but we're also giving energy to those water molecules. And so those water molecules are going to be able to overcome their interactions with other water molecules, escape and be a gas. They're going to rise up out of the water and leave all that goodies behind. What's going to happen though is that if that lid is cold, if the lid is hot, it's just going to go back down into the water. It can't stay a gas forever, and there's only a certain amount of water that can stay in the air. But if that lid is cold, the water is going to condense. It's going to basically hit the lid, transfer some energy to the lid, and just kind of like settle down and come back and be a liquid on the lid because the lid is cold. And so you're going to get more and more water escaping and joining this lid, leaving everything else behind. So we heat up the lid in order to prevent that from happening. As to what else is in the reaction, you're going to have things like magnesium and salts, which are going to help allow the polymerase to get to work. Magnesium is really important because because all that DNA is negatively charged. Remember all those phosphate groups, and so magnesium is really important for helping stabilize the interactions, allowing the polymerase to actually bind the DNA, bind the incoming base, kind of coordinate things and make it so that the reaction can happen. You also have your DNTPs, so the DNA deoxynucleotides to get added, pH stabilizers, things like this. Often these components are, you get them in sort of like a master mix, so it's all mixed together, and then you add the same mixture to each of your different reactions, where in each of those reactions you have the specific DNA, but then the rest is all the same. The rest is all then going to be given with this master mix. So some key things to remember are that you need to make sure you design your primers so that they bind only where you want them to bind and nowhere else. You set that anneal temperature based on the TM of your primers. So you want your primers to have a similar TM. And you set that anneal temperature so that the primers are going to be able to stay bound, but the non-specific things are not going to be able to stay bound. And in order to allow them to bind, though, you first have to melt the strands. So you separate those different strands. Then you cool it down a little, but not too far for the anneal temperature. Then you raise the temperature a little so that DNA polymerase has enough energy to go to work. You allow DNA polymerase to go so that it has long enough in order to actually copy the length of the product you want. And then you keep doing this over and over and over again in cycles, where each cycle you're separating the strands, allowing the primers to bind, allowing DNA to copy. Then you're doing it again and again and again, exponentially amplifying the amount of DNA. So doubling the amount of DNA you get each time, because each strand that you make can be used as a template for making another strand. And so at the end of the day, you can get a lot of specific DNA, but only if that DNA was there in the beginning, which is why you can use PCR for things like qPCR in order to see whether a specific DNA thing was present. Assuming, of course, that your PCR primers are specific enough, because if your primers aren't specific, then you're going to be just amplifying non-specific things, which is what we spent a lot of today's post about, how you can avoid that by designing your primers carefully, using a ideal anneal temp, using a hot start polymerase, and various things like that. So then you just program it into your PCR machine, get to work, and hopefully your PCR reaction works. If your PCR reaction doesn't work, the easiest thing to do is to try it again. Sometimes it's really easy to accidentally forget to add something, or to think you add something but you didn't actually, because you're typically adding really tiny volumes. So when you're adding those really tiny volumes, you want to make sure that when you're looking, you actually look and see the liquid go up into the tube and in your pipette tip, and then out of the pipette tip into the liquid. So pipette like into the liquid so that it gets drawn out. And then keep your thumb held down when you're pulling out of the mixture so that you're not actually sucking things up. You want to actually look at the tip to make sure that you didn't suck up the liquid, because it's really easy to like accidentally lose a little bit of the volume when you're trying to transfer, and then things aren't going to work. So if things don't work, try it again. If things still don't work, then you might want to be going into some troubleshooting. Are your primers designed correctly? Is your temperatures correct? If you're getting much non-specific products, maybe raise that anneal temperature. Maybe design more specific primers, longer primers, etc. And yeah, so hopefully your PCR, you don't have to do any of that troubleshooting because your PCR works ideally. And hopefully now you have a better appreciation of how it actually works. If it helps you, I like to think about PCR as a sort of like train reaction, where DNA polymerase is going to be like a train that can only travel, between any two cities, but it can only travel on single-stranded track and laying down the track ahead of it as it goes. It needs to travel with a single-stranded track, but it can only start when it has a full width track, so double-stranded DNA. And so this is where the primers come in. They act as a sort of station where they give the polymerase that double-stranded region it needs. And so this is kind of like specifying your start and stop, your destination and your start station, in order to tell the polymerase where to start and stop. And then basically you just control the conditions in order to make it so that the DNA tracks are separated, or your stations can bind, where the DNA polymerase, where you're trained, you give it the all go ahead, et cetera, et cetera. And so more on this analogy in past versions of this post, if this helps you. If not, just stick to the conventional and hopefully it won't steer you wrong.